In this lecture, we're going to continue talking about cutting plane algorithms. And specifically, we're going to take the approach that a cutting plane algorithm is an independent algorithm that we can use to solve an integer program. We're going to talk about Gomory's fractional cutting plane algorithm. Our particular example is going to be an integer program where we're maximizing some linear objective function, cx, subject to linear constraints, ax is less than or equal to b, and also having all the points x in the integer lattice. At a high level, the way this algorithm is going to work is we're going to solve the linear program. By solving the linear program, we're going to find a solution x. If x is an integer solution, then we're done. The linear program solution is an integer solution. However, if x is not an integer, we're going to add a constraint. The constraint we're going to add is going to cut off the particular solution x, since it's not feasible, it's not integer. The way we're going to create this constraint is with Gomory's constraint generation technique. To understand this algorithm in a little bit more detail, we need to understand a little bit about basic feasible solutions. Whenever we solve some linear program, and in particular the linear program we're interested in, we end up with a basic solution. In a basic solution, there's a set of variables, which we're going to index by b. These are the basic variables, and these are the variables that have a positive value. The other variables are the non-basic variables, and the non-basic variables have all of their x's set equal to 0. Basic feasible solutions are an integral part of linear programming. Given a basic feasible solution, we can rewrite our linear program in a particularly interesting form that's going to be useful for us. The details about how we do this rewrite aren't important. But if you do like some details, the basic idea is that given a basic feasible solution, we can take our non-basic variables, eliminate them from our program, and then find the value of our basic variables by inverting the matrix A. When we do this, we can write a set of equalities that tell us exactly what the value of our x's are going to be. In our rewrite, these equalities are our constraints. By doing this, we also can identify a new objective function where there's some constant plus all of the non-basic variables. Again, the details aren't important. What we should notice about this rewritten linear program is the following things. First, all of the constants introduced here are new constants that are derived from our original constants. Our original constants are the c's, the a's, and the b's. Our new constants are all written as a hats. A hats have nothing to do, or rather are derived from, the c's, the a's, and the b's. In our objective function, the only variables that appear are the non-basic variables. In our constraints, we've written, or rather isolated, all of the basic variables for it with its own particular constraint. For every basic variable, we've identified exactly one constraint, and this constraint has only this basic variable involved in it. We're going to use this rewritten linear program to find cutting planes. Now that we have our rewritten linear program, we can notice that if we're at a solution that's not feasible, we have at least one variable that's not integer. We focus on the constraint associated with this one non-integer variable. We take this constraint and we take the Gomory transformation of it. That is, we take the floors of the various constants involved in it. We can again remind ourselves of exactly how this constraint is created. We have a variable x that's an integer variable. We have a bunch of non-basic variables x that are also integer variables. We've taken the floor of some constants, which forces this entire side to be integer variables, or rather be an integer. And so we take a floor of the other side. We can then also take the original constraint, eliminate the variable xb from the equality, to end up with a new constraint. This constraint is derived simply by just doing algebra. We then define two new quantities. We define Fij and F naught j. Fij is, in some sense, the slack of the constants. It's the difference between the value of the constant and the floor of that constant. This is the same for both sides of this equation. Now we note a few facts. First, because xbu is non-integer, or rather fractional, we know that a naught j is going to be a fractional variable. And so f naught j has to be a positive value. This is the fractional part of a naught j, that is f naught j is. We can make a similar argument to say that fij also has to be positive for every variable. This follows from the facts of basic feasible solutions. In total then, all of these f's are positive variables. Now we note that each of the xi's that are non-basic, because they're non-basic variables, are all equal to 0. So the constraint we've written has 0 on one side and a positive value on the other. And so this constraint has to be violated at this particular solution. So at this solution x that our linear program created, we've now eliminated that solution from our linear program. Now, what we can do is add this constraint to our linear program and resolve the linear program. By doing this, we know that we're going to get a new optimal solution. The original optimal solution x is no longer a feasible solution. We can continue to do this iteratively until we get some x that's an integral solution and therefore feasible to our original integer program. This is the idea of how a cutting plane algorithm is going to work. We start with an original formulation and we continuously add constraints near optimal solutions until we get a problem that has an integral optimal solution. This is just one view of the cutting plane algorithm. We can also view cutting planes as an enhancement to the branch and bound technique. We're not going to go through those details here though.